what I'm going to show you today is a new feature that I added to GHC, and it was due to be released in the middle of February, which is past now, but it's going to be released in the next version of GHC, version 8.4. So it should be coming very soon. There are release candidates out there, but yeah, I would have liked for you to be able to fiddle with this immediately, but yeah. Anyway, so what is a valid substitution? So here we have our f with the type string to list of strings. And now, if you compile this with a new GHC, it will tell you a list of valid substitutions for that whole. So valid substitutions are things that you could put in place of the whole. So if you have your functions and libraries, they all have types, right? They're all very, very well typed, and we all know the types of the functions. So we can use that information to kind of look up. So what is it that we have in scope that could possibly fit this whole? Yeah, and so for this example, it will return this list. And I want to show you this graphic. So this is just a reminder about, so we have, functions in Haskell can be polymorphic. So if we have a whole of type string to list of strings, so we have an exact fit, which is just a string to list of strings, and it fits the whole exactly. But we also have kind of more polymorphic fits, which we also want to suggest. So you can use inits here because that takes a string is a list of characters, and it returns a list of characters, so that's valid. And if we're going to go into more type classic polymorphism, you can use return there, and we'll just insert the string into a list of length 1 with the string in it. So I'm going to show you now the demo. So this was the current GHC. But we have a freshly compiled version of GHC, and we're going to load the same thing, demo 1a. So this is what we were looking at, but if we load it now in the new GHC, and this is a demo, so it's probably going to break, but we'll see. Aha! I'm going to set a flag, which will make it do less output. And here we load again. Anyway, so here's the same list as before. So we compile the whole, we get the same information, we get the type of it, where it's located, but now we get this extra list of valid substitutions. And since we imported the list module, now we see that we can use the group function because characters, they have an equals type class defined for them. We can use, we can do permutations of the string. We can do subsequences of the string. So, and there's a lot of stuff, you already have a lot of information in your types about what you can do, but now you can use that to look up information you have contained in your libraries for your particular use case. So I'm going to show a bit more complex results. So no, this is not the thing, it's the B. So this is the same. So this was the, this is way too big, Max. This was the previous whole. Can you see it? It's a lot of output, but that's just because we have a lot of information. So, does it always jump down? No. Okay. So, if we have a function from which takes a character to bool, and we're giving a list of characters, and we're supposed to return a string, which is a list of characters, we can use these functions. We can use filter, which just filters the list based on the function. We can do take while and drop while end, and there's a lot of functions we can use. And already we know just from the type what these functions are. Anyway, we can do sort on because booleans are ordered, and then we have this mempty function which uses it's using the monoid instance for functions because lists are monoids. It can work out that. So mempty will just return id and then string. Anyway, And then because we gave this hole the type char to bool, and we imported the character module, we also get a list of things which takes a character and returns bool. And this is classic. You're gonna split, you're gonna filter out all the numbers or whatever, and you can never remember, right? What were the functions that I already have. So this kind of prevents you from redeveloping all these functions because you can just look them up. Then we have even more nicer things. So here we have a kind of a special hole. It's just supposed to return a string, this h function, and the whole. So this is show applied to the hole, but that means that whatever is in the hole must have a show instance because we have to be able to show whatever we apply because we apply the show function to it. So if you compile that, we get everything in scope that has a show instance. So we get the pi, which is, if you show pi, you just get 10 digits of it. You don't get infinite digits. We have the less than, equal, and greater than constructors, and then we have otherwise. And then there are some other more things in scope which have a show instance. So that's kind of useful. Right. And then another question is here, kind of, so another thing here is kind of, so we have these things right here. It's better to see it with the first instance. So let's load that again. 1A. So here we have a list of things which fit the whole, but it's kind of, because we're just showing the top 6 items, we kind of want to know, we want the most relevant substitutions first. So we do that by doing something called, so this is all found by doing something called subsumption checking, which checks for, it takes 2 types and checks whether you can put, whether the type that assumes the other type. So if it subsumes the other type, it can be used everywhere that something of the previous type could be placed. So it's basically saying if, so this is the type of char to string, and lines, the type of line subsumes this type, because you can use, this is the same type, but everywhere you have something of this type, you could use something of type EQA to A2 list of A's. So, and we sort the output by kind of doing subsumption checking for all of the results. So we see here that group subsumes lines and words, and init subsumes group because group has this extra equality constraint. Otherwise, it's the same type. And we can show that by this graph here. So we have these, words and lines had the, they were at the top. They had the exact same type. Then we had these init, read, and fail instances, which you would have seen if I'd enabled the entire output. Let's set that flag, set F. So it also, you can also not show everything. Let's have no max. No offense to max. Yeah, so here we get more things. We got the previous things, this is just up there, and we get these repeat functions. We get the mempty weird function. We get all the monad applicatives things. We get the fail function, and because we can, it's applied to string, and it will just return an error. We get the error and error without stack trace because these are kind of very polymorphic types. You can, like especially undefined, you can put undefined anywhere. And in the latest version, which I would like to show you, but I'm too afraid because it's even more buggy than this thing, we also filter out these kind of error without stack trace because they're almost never what you want, right? So, but it's good to know that it finds these things. Anyway, so, but here's a new cool thing, and it's called refinement substitutions. So if any of you know Agada or similarly dependent, similar languages, they also have holes, but they can do kind of more things than just suggesting a single identifier. So like if you're writing the sum function, you might want, it has a type list of integers to integer, but the sum function is defined as fold L plus 0, like Mary talked about this morning. And then you have this fold L1 max. So if you're writing the maximum function, which finds the maximum of something, then you'd probably write fold L1 max, which takes, it doesn't take an identity element, but it just uses the first element in the list. So it doesn't work for empty lists, but it's hard if you don't have any. If your type is not bounded, you can't really do this maximum thing without. You need a bounded constraint. Anyway, but how does that work? Well, that's not going to come in this GHG. That's going to come in the next one in 8.6.1, which will be out this fall or summer. And then you get even better substitutions. So instead of just saying you can place sum here or product, it says, well, you can use fold L1 applied to something of the correct type, which will then, if it's applied to the correct type, it will have this resulting type. And it can also do more than one extra arguments. You can also do with 2 arguments, and it goes up to n, but the larger the n, the longer it takes to search. So we do that by setting a flag called refinement level substitutions equals 2, and this will tell it to. So when you encounter a hole, do not don't only just give me. Do not only give me the valid substitutions, also search for these refinement level substitutions. So if we have some examples of this in, like here. So here we have a function f list of integers to integer, and it's some function applied to 0. And what happens if we load this? Well, we get valid refinement substitutions. So it produces a lot of output, so maybe a little smaller. Can you still see this in the back? All right, good. So we see the entire output. So we have the whole. It's of type, since it's applied to 0, it's of type integer to list of integers to integers. We see the valid substitution. So you could have the constant function, which just ignores the list and just returns the integer you put in, or undefined, of course. But then you could also apply fold R and something else, and fold L and apply it to something else. So this kind of assumes that if you find something with the correct type, like A, B, and B, so in this instance you'd have to give it a function of type integer to integer to integer, then it will work itself out to be the correct type. So this way you can even search. You're not even sure, like, it's very, like I said before, it's not often the case that it's just one function you're looking for. You're often looking for a function. You might want to get line from some server, but it needs connection information or whatever. And then this would also find that, and you also get weird substitutions like head. So if you apply head to a list of functions that would have the correct type, then it would work itself out to be the correct type. But yeah, that's not really useful. But it's kind of hard to filter out these things because they are correct. They're just not that useful. We also have these. We can also do this with 2 holes. So yeah. So if we search for. So here we omitted the integer initial. So instead of searching for f applied to 0, we just search for anything of type list of integers to integers, and it will tell you that you could use fold R applied to 2 holes or the fold L1, fold R1 functions. So yeah, that's kind of useful. All right. Yeah. So here we have the demo. Anyway. So how is it done? Well, the previous speaker talked about free variables. And what we do is we kind of, what we do is we use the built-in machinery in GHC to, so when we encounter the hole, we take its type, we go through everything that's in scope, and we just, run the type checker and see, if I place something of the type of this thing in the hole, would it work itself out? And for the refinement substitutions, we just add kind of new variables which are never mentioned anywhere else, which are then, completely free variables. And then we allow it to kind of unify it with anything. So it's all based on the existing machinery inside GHC, which means that we can handle even, hard things, not just kind of toy examples like these things, but we can handle things like lens, and we can do things with advanced type system features like type families and stuff. So I'm going to show you an example of that. So go into the typed holes. So here I have a anyway, here I have a module implemented, and it's using the lens library, which is everyone's favorite library, of course. And it's kind of known for being, it's hard to learn, it's hard to understand, and it's got a lot of, things with weird types, because, it's all very general, and you're not sure how it works. But what we can do, so here we import lens, we import some control monad state just for nicer output. We create some, toy example type, which is just called test. And test has something of, text has a field called value in it. So it's just a container for this value. And then we define a lens to operate on that value. So this is the value lens. And through some type level trickery, you can use this to access things. You can use it to, or it's kind of a way to. So you have this structure in the test type, and you can use the lenses to kind of zoom in on parts of it. And if you zoom in on the correct parts, then you can update those parts, or you can or you can read those parts, or you can do whatever. So we're going to try it out. So we have this update test function, which just takes the test thing. And lens has this kind of, it's supposed to be useful, but it's just kind of confusing also. It has this and tilde operator, and then you can use the do notation to do your updates. And that's nice, but we just heard about this, and we're like, okay, let's try that out. And that's we have this. We're gonna do something with value. I'm gonna try and add 1 to whatever's in the value. And then if we compile this, let's do it. So we have to do cabal new build because we're using the new features of cabal, and we allow newer because since this is done with the latest version of GHC, there's this thing called the semi-group monoid proposal, and it kind of breaks everything already on Hackage. But they've applied patches to it, so if you do some Hackage package project trickery, you can make it work. But you need to use cabal new build. Anyway, so we try to build it, and fortunately I've already built lens, so we don't have to wait for 3 hours to build lens, but it's good. So it found this hole. It didn't do the uncluttering, but that's okay. Oh, well, wait, it did. Okay, so here we go. Aha. So we had this hole. It's of type. So yeah, and this is the thing with lens, right? It has this weird type. It's like integer to f0 of integer, and you have 2 ambiguous type variables, and takes test to f of test, and it are you gonna and this is kind of the thing that if you're working with things like Google, which allows you to look up things in all the packages, and it's really nice. If you're just starting out with lens, you have no idea okay, so if you just copy paste this into Google, it won't work, right? It won't know whatever these ambiguous type variables will be. But since we're doing it within GHC, we already know all the constraints that all the type variables have to have. because they're all inferred. So, and it figures it out. Okay, yeah, so whatever you could place here are these things. You could do the percentage equals thing, which just puts stuff in. And it's like, this is also the case with lens. Like, who remembers the less than hashtag percentage equals operator? You can't Google for it because you're like, I don't remember this name. And are you going to be looking for monad state, SM, A lens, SS, AB, AB, MB? But it's nice because, the compiler knows all this, and it's already implemented in lens, all these type things. But yeah, now you can look for them. But then we think, okay, we're not going to just do the +1 thing. We're going to, and then, it spits out more errors because it doesn't even know what these ambiguous type variables are supposed to be. But that's okay because our search doesn't really care. Then I'm going to show you a different hole. So we're like, okay, wait. I mean, we're doing integers. We're pretty sure that lens knows how to do things with integers. So we're just going to, okay, so now you're refactoring. You already have all the types. And you just want to see, okay, what happens if I just look for something that just takes the value and like how much I want to update it by. All right, let's try that. And we build it again, and then, yeah. And then we get these things. All right. So it turns out that you can do plus equals in do notation. So that's nice. And then we're like, okay, yeah, that's probably what I wanted. And this is the the good part about so it's a good and a bad thing because especially in the Haskell community and maybe it's also wider in function programming that they're like, okay, I've given it a type and it has a name, and then people just assume that that's enough documentation. You don't need to write anything else because and it's okay for things like plus equals, but it's not okay for things like less than hashtag percentage equals. But so here we found a substitution. It has the name plus equals, and the type looks okay, I guess. I don't really know, but then we can just try and put that in. What happens then? Well, I'll have to show you a valid substitution in action. So do plus equals, and so of course this is an operator, so we could do it infix, but we're not going to do that because it found it like this way. And we build it. Yeah, and the vim is incorrectly configured, so it uses tabs instead of spaces, but that's okay. So, and then so it type checks, and that's what we wanted. And I think that I can run it by doing some dist new style thing. Build. This is why tab completion is a good thing. Anyway, aha. So it ran it on a default value of test value 0, and it updates things to test the value equal 1, which is nice. And this is exactly what we wanted. So yeah, this was the lens demo. So and this is kind of the motivation for the library. Like you want to work with libraries like lens. We all, like maybe not all, but if you're working with things like databases, especially like the persistent things, it always has these weird constraints on what the database should be able to do. And you have a variable that's a database, and it should be writable, and it should have master privileges, and it's all expressed in some type class constraints. And it's it's really hard to look for these things live. But we can also, since we're using the built-in machinery, we can also do even more complex stuff. So we're going to take a look at a library called DCC. And does anyone know what DCC is? Does anyone know what the dependency core calculus is? No? I'll explain it to you. So what DCC is it's a way to kind of, it's called information flow control. So what you can do is that you have things which are annotated with types, and these types tell you kind of the privacy of that information. So what you can do is you can like when you're programming a web server, you can get the password from the user, and then you can mark it in a type that says this is not, this is private information. And then whenever you run your program or compile it, it can warn you, or like not even just warn you, it can fail with a compilation error, like, hey, you're trying to write the password here to a file, and it's not public information, so I'm not going to allow you to do that. So we have an implementation of DCC written by Max and Alejandro, or Max and Max is there, and Alejandro Russo is at Chalmers. So you go into here, and it's just, what, 13 lines of code, you said? Accepting the accepting the language extensions.
So do you need to put it on a slide and you want to brag about how small it is?
Yeah, so we had to add this semi-group thing because of that stuff. Anyway, so it has a lot of these type families. So we define a. Okay, I'm sorry. I don't really know how well things but does it, like, who here knows type families? Okay, not so many. Anyway, type family is basically a function on types. So here you say, so it's a type level function. So instead of just applying functions to values, you can also apply them to types, which gives you new types, which allow you to do more complex type checking. So here we have the type family protected at, and it takes a type, which is just star, and it takes L of kind. So how many people here know what kinds are? Okay, a little more. Anyway, L is of kind lattice, and this is a very recent addition. It's the type in type thing. So a lattice is, anyway, it's a lattice of types. So it has you know what a lattice is? So you can have like some top value, and then it can branch out, and then it comes back to some bottom value, and that's kind of a lattice. And this lattice is very simple. It just has high and low in this toy implementation. So, and this protected at type family, it kind of works with some types and checks for whether it's allowed to do things with it. So you run protected at, or you don't run it, it's just run during compilation. But if you apply it to something of type L prime, so here's another type. It's a T type, and it has it's L lattice argument, and so this is like, so what we do with these privacy annotations is we put them on boxes and not just directly on types. So this is the box for the lattices, and you can use this to kind of check for whether things are allowed. So this is the machinery behind checking whether things are public or not. And yeah, it's a bit complex, but it doesn't really matter. I just wanted to show you the kind of because the implementation isn't so long. So here we have something that uses DCC, and that's much more simpler because we don't have to worry about the implementation. It's kind of like that machine learning talk yesterday where, if this is already implemented in the compiler or in the library, you don't have to do it yourself. So you're less likely to screw it up, but if it is screwed up, it's way harder to get it fixed. So that's the other side. Anyway, here we have something that uses DCC. So we have a location type, which is just a pair of integers. We have a type representing restaurants. And they have names, they have coordinates, which are these location things, and they have ratings, which is just an integer. We have some user, so this is kind of the idea is kind of a restaurant finding app. So you have restaurants and you have users, and we know their location and we know how old they are. We can look up restaurants, and these are restaurants in Gothenburg. And then, so what we do here is that when you get the user, like information about the user, we should do like this. So when you get information about the user, we mark that as like it's highly secure. You're not supposed to be leaking information about the user, and this might include passwords or something like that. But yeah, we mark the user value as high, but we allow the reading of public information. So that's this read public constructor. So, and what we want, so if you have a user, like, if you get information into the system, you want to be able to use it somehow. So we have functions which go from something that's highly secure to something that's not at, like, you go from private information to public information. So, like, if you have a user, you can check, is he in Gothenburg? Is he allowed to drink? And then you can look up these best nearby restaurants. But why I'm showing you this is, so let's say you're a user of this library, QA main.hs. It's example.hs, yes. So let's say you're a user of this library, and you're like, waiting for, you're like writing, the manager comes in and he's like, okay, so we're going to use this DCC thing. It's highly secure, highly recommended by the best people. And you're like, okay, yeah, and then we have this implementation of restaurant information. And I want you to use that to make the app. Then they're like, okay, and you're like, okay, sure, I can get this user info. But you don't really have an idea of how DCC works. So you're like, okay, I have this, I got the information about the user. And then, I have this user thing and I want to get some information about it, but I don't know. I have no idea of, like, what can I do with this information? But then you can just compile this. You just put a hole, like, you just ask it, like, what can I do with the information about the user? And if you compile that with this thing, so you do GHC, no, we have to do ... in place bin GHC stage 2, because it's freshly built. Compile the example, and it gives you a lot of ambiguous type variables, because it's trying to print something that doesn't know. This is also a cool flag. It's called reverse errors. And if you're giving a talk, it's good because you probably want to show the first error, not the last one. Anyway, so we have a hole. There's a very roundabout way to getting here, but we have a hole. It's of type highly private information of user, and you want something that's public, and you don't care what it is. You just want something that's, you just want to know, what can I do with this information? And then it looks for valid substitution, and it says, yeah, okay, so here are the functions which allow you to do operations on these highly secure values and get something that's public. And this is really, so, and this is using type in type, the latest thing. It's using type families, it's doing, all that jazz, and it still works, right? And I think that if you're going to do this with Google, it would be, way harder because you'd have to write all these things up. Anyway, so that's the demos. Here's my conclusion. So we'll have time for a couple of questions. They're good for beginners. Like if you don't know the prelude, you can discover folds. You can discover things like fmap. And it can kind of, you just have the types. And they're all inferred by GHC. And you can use all that information to help you learn Haskell. You can deal with like hard libraries like Lens, which you wouldn't, like, even if you're an advanced user, you can still useful for this for that purpose. You can use DCC in this thing to write secure code, so that's cool. And they're in GHC, so you can. I wanted to say, try it out now, but they haven't released yet, so try it out in a couple of weeks. That's the valid substitutions. And then there are more, the refinement substitutions are a bit later edition, and they'll be coming in 8.6, but they're already available on the head. So if you go pull the GitHub repo and build it, you'll be able to use refinement substitutions, but you'll have to do all sorts of workarounds because of some proposals. All right, questions? Other questions? Yeah.
Hey, great talk, thank you. Is there any way that we could integrate this into like HDevTools, GHCMod, something like that, so we could have it available in a editor or IDE?
Yeah, so that was the idea. So you know, this kind of probably gonna, because it's very easily parsable output, it should be very easy to kind of write integrators like IDE plugins and just, you know, instead of the classic, you start writing something that will suggest things that have the same name. Now you can just put a hole there and it will suggest things that fit the hole. So that's quite useful. And that's also, you know, that's why you have these no max flags, just so, you know, if you're an IDE, you want to be able to show everything. So yeah, and the GHC mod, it should probably be easy to get in there too, but I think, yeah, at least when I tried GHC mod last, it was kind of outdated, so it might be a bit kind of bit rotted right now, but yeah. Okay, more questions?
Yeah, hi. So how do you make these substitutions, I mean, the recommendations for substitutions? Is it just everything which matches in scope, or is it ranked somehow?
I mean, so it's everything that's in scope, but it's ranked by the substitution thing. So, now the subsumption thing. So what I do is that I build this, oops, this is not the button. Anyway, I build this graph, right? So you had all these suggestions. You had the word suggestions, the line suggestions. You had inits, read, fail, repeat, return, empty. You had all these suggestions. They're very, you know, you don't just want to output them in the order they were defined. You want to kind of show the most useful things first. So we build this graph. So this graph works like, so if something is subsumed by something else, it has a link to it. So words is subsumed by inits and read and fail. So that's why it's, so those are these things. Repeat subsumes inits. Empty subsumes repeat, and return subsumes repeat. And what we do is then we do a graph sort. So things which are things which have links to things that are later in the graph become earlier in the list. So, and that's kind of, you know, it's a one way of ranking it. But you know, it's future work to add kind of, you know, ranking by module or kind of ranking. It's just it's because it's you know, this is an easy question to answer, like do they subsume each other? But it's kind of, it's a hard question to answer, like what's the most useful suggestion? You know, the most useful suggestion is the one that the user ends up using, but it's a very you know, ill-defined concept. So, but we do the thing that seems good, and then we just hope for inspiration later.
And how do you get everything which is in scope? Does GHC help you out with that?
Yeah, I mean, you get errors when you use things that are not in scope, so it just has a list of everything that's in scope. Yeah.
Thanks.
Are more questions? Yeah.
Hi, thanks. So in theory, if you had some test to run, you could also say which one is the right choice in a way. Is that something?
Yeah. So then you're going into property-based things. So and that would be really useful, but it's kind of hard. So one problem that we have is kind of, it's hard to impart information about the whole, right? Because you just have the identifier and its type, and it's kind of hard for you as a programmer to kind of tell GHC, so I have this whole, it's called A, and then I want you to parse some other file which contains properties for the whole A, and it's anyway, it's incorrect code, so you wouldn't really use this. So it's an error to have a hole in your code. So you want, yeah. So it's hard, yeah. Yes?
So I would really like to be able to run that code. You say it's erroneous, but it's not really. You've got 6 alternatives, all of which pass the type checker.
Yeah.
I'd love to be able to take that function and call it, and then have GHC say, well, if you put lines in there, you get this answer. If you put words in there, you get that one, and so on.
Yeah.
So it'd be nice to actually be able to play with the alternatives and see which one you want. And that doesn't demand parsing properties. It just demands being able to run the code afterwards and to indicate which one alternative you want to try.
Yeah, that's a good point. Yeah, but it's still, yeah, it's hard because you're already in the error state. You've already dumped a lot of error information, and then you kind of want to start running things again. And if you want to hear a kind of a secret, that GHC it's kind of just a bunch of things duct taped together, or like it's well written, right? But there's a lot of side effects, and there's a lot of stuff going on, and it's just really hard. And it's not like you can just run this as a pure function and then take the output and run something else on it. It's really deeply integrated into the entire thing. So yeah, I would like to do that certainly, but it's hard to do it in GHC currently. But I think that something better would be to pipe this out to some external tool like GHC mod, and then you could have GHC mod run these things. Right.
Okay, any more questions? I think we have time for one more question.
Okay.
Okay, thank you.
All right.